So we come back to the question, when does a function f equal the sum of its Taylor series? If you think about it, way back at the beginning of this chapter, we said if a function has a Taylor series or a power series representation, it can be represented by that Taylor series formula, assuming all those derivatives exist. But that was a big if, wasn't it? Yeah. Well, okay, here's an answer to that question. When the limit of its partial sums, Tn, remember the nth degree Taylor polynomial is Sn in disguise, right? When that converges to f of x. Okay, so we use Tn to estimate f of x, right? So when Tn converges to f of x, we say that the function f equals the sum of its Taylor series. Now there's an equivalent way to think about that. If we define f of x minus its Taylor polynomial approximation, nth degree Taylor polynomial approximation, if we define that as Rn of x, R stands for remainder here, then what we want, remember earlier when we used that 6th degree Taylor polynomial for cosine to estimate cosine, essentially, which is really estimating its Maclaurin series. Remember how accurate that was? So the difference between the cosine and that 6th degree polynomial was close to 0, wasn't it? So the idea is that if Rn, the difference between the actual sum, f of x is the actual sum, and the nth degree Taylor polynomial used to approximate that sum, if that difference goes to 0, as n increases, exactly what this is saying, the limit as n goes to infinity of Rn of x, if that equals 0, then f will equal the sum of its Taylor series.